Hi, welcome back. So we're in chapter 5, prediction by probability, at the outline of univariate concept of probability to discuss the probability of a continuous value. Now what we're going to do, actually, we're going to start discussing special kind of distribution, given that the variable is a kind of continuous type of variable. The first one we'll be looking is the easiest one, something called uniform kind of distribution. In every distribution we're going to discuss, we will be looking at deriving the idea of the probability density function of that distribution. It's a cumulative also distribution function. Maybe we can also look at the mean, the sigma and sigma square, the variance and the standard deviation. Take, for example, this variable x. If we look at variable x, we discussed one of its main properties, the range of value x. Well, when it was a discrete, we had a whole number of 1 and 2 and 3. Maybe it goes to infinity or uncountable number, but it still is the whole number. But when it comes to actually the possible outcome of a variable x, given that it's a continuous, it means the range of x in an interval between two values of a and b. So every possible value can be taken between a and b. It's a possible value that belongs to the range of the x. Let me start talking about a real example and try to derive the idea behind it. In a certain time of the year, like say between the second month and the sixth month of the year, waiting time is the same. You will wait the exact same amount of time. Doesn't matter you came early or you came late, you came in the second or the sixth or the third, fifth, whatever. You will wait the exact same time. Now, from visual perspective, so the total area here, it's going to be 1. What I know about the area of rectangle from geometry, I know this piece of information. Now, the question is, what is my base here? Well, my base is the difference between B and A. And what is my height here? Well, my height here is going to be the value of f of x, which is the probability. Another way to say, if I substitute all the information, I get the area here, the probability f of x just equal to 1 over b minus a. So this is my PDF, a uniform distributed variable, 1 over 4 probability of waiting, given that you applied in any time between the second month of the year to the sixth month of the year. If I want to look at the mean, that is a uniform distributed, is going to be the integral from a to b, x multiplied by the probability density function. Now, the same thing, you can look at it from the variance perspective. That is going to be the expected value of x squared minus the expected value of x. But the point is, we need to find this expected value that is equal to the integral from a to b in the x squared multiplied by the probability density function. And if you take actually the integral of this term, 1/3 by b squared plus ab plus a squared. And if you put all together, the sigma square is going to be equal 1 over 12 b minus a, whole term is a square. And sigma, of course, would be just the square root of that sigma square. The cumulative distribution functions, actually by looking only at the graph, I know that x minus alpha multiplied by the probability density function, which is 1 over b minus a. And that's why I could write the cumulative distribution function of. So we have derived actually the probability density function, cumulative, sigma square, and also the average mean. The next one we will be looking at exponential distribution. Well, the exponential distribution is one of the widely used continuous distributions. It's often used to model the time elapsed between event. It's said that its PDF, the f of x, is equal to lambda by e to the power of minus lambda x, whereby x larger than 0. And 0 actually is going to be otherwise. This is the PDF, or the probability density function. And from there, actually, it has derived function of the CDF 1 minus e to the power of minus lambda x. And it said also the mu, or the expected value of x, 1 over lambda, and the variance is equal to 1 over x squared. This information that you have at hand, it's all what you need to know from any academic book, material you study, given the variable exponentially distributed. All over the questions to give you
some kind of average or the mean, and then you calculate. In other words, say mu is equal 1 over lambda, or you could say other way around, lambda is 1 over mu. And here we go. And then I can ask you a question. So I'm going to share with you right now, how did I reach out to create my own equation to calculate the probability given the variable x is distributed exponentially. To start up with, I would like to give an example. You are at some station and a number of buses arrive, 2 buses every 1 hour. I don't really like to name the unit specifically, which can cause a lot of confusion afterwards. So I will just have 2 units come every 1 unit. I don't want to talk about the time here in terms of hour, but I want to talk about it in terms of minute, or maybe in terms of second or millisecond. So I will say 60. And the 2 remain as it is. Next thing I would like to do, I want to translate this into much more a mathematical intuition. So as if I'm saying 2 over 60. So basically what I would do, I would take 1 unit of this, which is half of this. And of course, you have to correspond to the denominator here. Take half of this, which is going to again be 30. I want to look at this value of lambda from a kind of a different aspect. Imagine it represents a success. It means the 1 minus the lambda, it represents the opposite of A is the NA. I got like this time point like this, okay. What it says actually here, it says that at each point here, there are 2 possible things to happen. A could happen or the NA could happen. And you just arrived in this elapse of the time between the 0 and the 1, exactly the bus happened to arrive. That means you hit the A here. It's over. You take the bus and the entire problem we don't need to discuss anymore. This one, if this scenario really happened, you win the 130. Let's take another scenario. To the second elapse of the time of 2, I mean, you are in 2 because you lost 1. Another word to say, your quantity, total chance of this 130, and which is multiplication in the word of probability, what you have lost before, which is going to be 29 over 30. Imagine the reality. Now we are looking backward, okay? And we are now doing the question from the beginning. Now, this is a future, okay? Imagine you actually caught the bus at 5. So my question is, what are the chances or the calculation involved of this A and NA? You got the A at this 5. It means the 4 and the 3 and the 2 and the 1, all of which actually have been towards the 29 over 30. So each one of these represent the total element or space. This is the logic. That's why I am multiplying at this time of 2, the current value of A, this is what we are interested in, with what you have missed before, which was 1. If I draw a kind of a line here, represent this is my t, and this is the values, the sum of them. Okay, I will call them the y just for now. At the first point, maybe from 0 to 1, you could even imagine, I mean, you got to this value here, 1 over 30 here, or the A. And then every point I move over the line of that time, point here is going to get lesser and lesser, kind of a curve in that way. What is the PDF of this? My second question is this CDF, the cumulative distribution function. It is actually the sum of each term here, k from 1, okay, these are the k values here, all the way to the x that you are interested in. Not hard to figure out the intuition or the pattern. That is lambda multiplied by 1 minus lambda to the power of k minus 1. Well, I'm going to use some skills of algebra. I will call this entire left side as S of n, for example, for now, which is equal to cumulative distribution function of this exponential distribution. It turns out to be actually nothing but 1 minus lambda power of x. Capture this area under the curve here. If you look at the book, actually, CDF is equal to 1 minus e to the power of minus lambda x. You can see my difference of intuition here. The integral from 0 to x of the f of x, probability density function, the PDF, we actually integrated this to reach out to this. Now, if I want to go back actually to figure out what was the PDF, what shall I do? If I take the CDF derivative, I will get to my PDF. If you go and check what is the derivative of this, it's going to actually look like this: 1 minus lambda power of x multiplied by the natural logarithm of 1 minus lambda. Now, this is going to be your PDF. This is the way that I construct my own PDF. From the book, this PDF that I'm showing you, it looks like lambda by e to the power of minus lambda x. Now, this is the f of x from the book for the exponential distribution function. It's like this. Now, this is the way I inducted. This is the way how the book is showing you. You will see now we're going to do tests to see how far away from each other. Reach out to the last one is the expected value of x, well, 1 over lambda, and actually the variance of x, 1 over lambda square. Let's try to discuss actually a real problem. And I'm going to show you the book equation of the exponential distribution. This is what the book says. Now, our equation, what we have actually reached out to, let's actually do the problem of the 1 over 30. Let's try to see some values of x at 10 minutes, x at 5 minutes, 30 minutes. I'm going to show you both sides. This is online calculator for the exponential function with lambda equal 1 over 30. And just can you choose the values of the x as you like. At the same time, I have written short code here in Python. Let's actually do this and see what are the information we get at 5 minutes. So at 5 minutes, I am expecting 15.6. See, you see, it is kind of a line. It's not the curve exactly because the span is very small. It's just only 5 minutes. Now, these are the information according to our calculation. And this online is using the formula as the book is indicating. Let's put 5 minutes here. What you get here, you get the probability of x less than 5. It's 15.35. Our finding was 15.6, so it's almost identical with a very small margin of difference. And this is the complement, of course, 84.4, or it's going to be here 84.6. It's exactly the same. Okay, let's now create a larger interval. Let's make it at 10 minutes here. Look at the values here: 28.8, 71.2. Let's actually change again x here to 10. Again, 28 point. It's almost the same exact result as I have done my own formula anyway. Let's try to make this one exactly 30, which is equal to the span of the time elapsed. 63.8, 36.2 is the complement. Now let's get this one again to equal to 30. You will get the value exactly almost identical to our finding. My formula, it turns out that the larger the interval, the more I get closer to the actual formula. And that's why in the actual formula, you got this E presentation. And now we are ready actually to move to the third special kind of distribution. It's called the normal distribution or the Gaussian distribution. In any distribution so far we have discussed, especially given the variable is continuous, variable x and happens to be normally distributed, given that there are some parameters, mu and the sigma square. This is the original PDF. Shape actually would look like this. This is called the normal distribution. This was based on a mu, as we said, and sigma. The idea introduced to get a better or easier way of this presentation. How about if we think about creating this graph, however, instead of using the mu of the population, we take parameter, let's take it at 0, and then the distance is going to represent a standard deviation. Each point is away by 1, 2, or 3 standard deviations. Well, if I am at 1 standard deviation away from here, my data like this. If 2 standard deviation like this, maybe 3 standard deviation like this. And this is what's so-called the Z distribution, actually. Just by taking the exact same equation, reintroduce it. This is a new PDF. There are tables called the Z table, actually giving you the exact, okay, I am 2 standard deviation away. Well, this is the Z value. Then what's the probability, 0.05 or whatsoever.
the number of distributions are available there quite a lot, and you might get lost if you really dive deep into each one of them. That's why I think personally that understanding the concept of probability and the principle of distribution produce the right solution. Otherwise, memorizing formula doesn't really help. You don't really understand the question and what you're trying to find out. I would like to speak about gamma distribution. Needed two parameters. Alpha parameter should be larger than 0, and the lambda parameter also should be larger than 0, which is going to be shape of the PDF. Now, what does this alpha represent? Actually, the number of occurrence. The PDF is given in this case called f of x. Now, this particular formula of gamma have three important terms. This is the first term, the second term, and the third term. Let's try to fix this alpha to be equal to 1 and try to plug in to the formula. And that's all reduced actually to lambda e minus lambda x. And this term is going to be equal to 1. I will explain why. So what's gamma function is nothing but actually the n minus 1 factorial. For example, if you say the gamma of 5, that is exactly as you are saying the 4 factorial. It might be interesting to say, why would you want to create a function to explain that? Well, the idea actually behind gamma function was, imagine if I tell you the gamma of maybe 3.8. Now, here's the story, how you're going to actually find the factorial number of something is not completely integer like that. And this is where the gamma function, actually, the formula of gamma function have come to play. And the actual formula of gamma function is just equal to the integral from 0 to the infinity of x to the power of alpha minus 1 multiplied by e to power minus x. And this is a very strong, actually, function, in my opinion, because if you plug in this function given any gamma, you will get a graph. Maybe depends on the value of alpha. And then it turns out that what you're trying to find, for example, it will be the area under the curve. So this is the power of gamma function anyway. So another word to say, the gamma of 1, that is the factorial of 0, which is 1. That's why this term go to 1. When alpha is equal to 1, we actually end up with only this. And what is this? This is the exponential distribution, if you remember we just discussed before. What we can conclude, the exponential function, it tells us discussion of one of these objects that we are talking about and the time of arrivals that can take. So we're talking about one of these objects. However, if we are interested to talk about not only one of arrivals, maybe more than one, maybe 2 arrivals, 3 or 4, or whatever number of objects, but still we are talking about the same exact time period. Here is the alpha, and here is still the lambda we were talking about last time. That's where gamma actually is more general form of the exponential function, given that alpha can be larger than 1. So that was all about the gamma distribution. The idea is still, as we said, to understand the PDF, to understand the concept of extracting depends on the problem. The next one we will be looking at the outline bivariate concept of probability. That's exactly what we're going to do next. I will see you then.